Alrighty, let's look at some questions on momentum. There's a lot of kinetic energy questions with the momentum questions because they do kind of go hand in hand because they both consider mass and velocity. So let's think before we start what goes on in momentum. We've got the two formulas, P equals mv, and then we also have the other one that says, goodness me, that didn't look very good, does that? That says F net delta T equals delta P. Okay, so that's your impulse formula. And then if we do kinetic energy, we're also going to look at EK is a half mv squared, and the energy comes into it because collisions can be either elastic or inelastic. So if we look at the first one here, an object of mass m moving in a velocity v collides head-on with an object of mass 2m moving in the opposite direction at velocity v. Immediately after the collision, the smaller mass moves at velocity v in the opposite direction and the larger mass is brought to rest. Refer to the diagram below. Ignore the effects of friction. So if we ignore the effects of friction, we can assume that we have an isolated system, and we should look for an answer that says momentum is conserved. We could check here by doing the maths. Okay, so this one is mv, and if we say this is to the right, this one is 2mv, but it's negative. So the total momentum here would be, if we add these two together, mv minus 2mv is minus mv. And if we have a look over here, after the collision, the mv here is going to be 0 because the velocity is 0, and the momentum here is minus mv. So that shows us that you realize I'm saying to this direction is positive, yes? Because momentum is a vector. So the momentum is conserved, which leaves us with A and C, okay? Then we need to look at the effect of the mechanical energy. So the mechanical energy is the sum of the kinetic and the potential energy, but there's no potential energy change here because they aren't being lifted above the surface of the Earth. So we only need to look at the kinetic energy. So if we look at the kinetic energy, it's a half mv squared. The kinetic energy of this is 0. But over here, we've got a half mv squared and half mv squared. And because both of these have a value of velocity, this is going to be two positive numbers. Yeah, this will be two positive greater than 0 numbers. And this will just also be the positive greater than 0 number, but this will be 0. Okay, so the kinetic energy, the mechanical energy, it can't be conserved because if I've got a plus and then a plus and a 0, this one is going to be greater than that one. So the kinetic energy is not conserved. So the answer here has to be C, because the mechanical energy wasn't conserved. Now it says to you, a person drops a glass bottle on a concrete floor from a certain height and the bottle breaks. The person drops a second identical glass bottle from the same height onto a thick woolen carpet, but the bottle does not break. Okay, what is the carpet doing? The carpet is slowing down the contact with the floor. Okay, it says which one of the following is correct for the second bottle compared with the first bottle for the same momentum change. So momentum change is mvf minus mvi, and it is equal to, which is the same as delta p, yes? It's the same as F net delta t. So if the momentum change is the same, if this value remains the same, why is the bottle breaking? The first time the bottle's breaking because it comes into the contact with the floor for a very short time. The delta t is very small. When we hit the carpet, so the floor has a short contact time, the carpet has a large contact time. So we're looking at one of these two answers here. But this value remains the same. The delta P remains the same. So if the delta T decreases, if the delta T increases, then the F net has to decrease. And that force is what's breaking the bottle. So it is a smaller force with a bigger time for the same change of momentum. So the answer here is a smaller force with a longer time. So the answer is D. let's go move on to the next question if my computer cooperates. Let's have a look. What's the next question? Okay, let's hope my computer's cooperating. It says a trolley of mass m is moving at a constant velocity to the right on a frictionless horizontal surface. A ball of clay, also of mass m, dropped vertically, falls onto the trolley at time t. So what are we doing here? We are changing the momentum of the trolley by changing its mass, okay? Because the ball of clay is sticking to the trolley. We had mv, and now we've got 2mv, okay? But this ball of clay dropped vertically downwards is not going to change the direction of motion. The trolley is going to keep on going to the right. And this is important because why? Momentum is a vector. And we've got graphs here, okay? So what do you think will happen if you make the trolley heavier? The chances are that the velocity will decrease the moment you make it heavier, okay? So, because that's generally what happens. So which one of the velocity time graph below correctly represents the velocity of the trolley before and after time t? I am immediately going to cross these two out, the ones that cross the x-axis. Because if a velocity crosses the x-axis, it means it has changed direction, okay? This trolley is not going to change direction just because you drop some clay on it. So then you have to decide here, okay, what is going to happen when I drop the clay on it? Is it going to go faster? Can you see this one here? Or is it going to go slower? And the short story is it is going to go slower, so the answer is C. Okay, now we've got ball P and ball Q of the same mass are dropped onto a concrete floor. Both balls hit the concrete floor with the same speed. Ball P rebounds with the same vertical speed. So if the speed before the collision and the speed after the collision are the same, then this must be an elastic collision, okay, for ball P. But ball Q has slowed down. It rebounds with the speed a half v. So Q cannot be an elastic collision. It has to be an inelastic collision because obviously the mass of the ball is not changing. And kinetic energy is a half mv squared. So the thing that we're changing is the v here. Okay, so it says which one of the following statements regarding the collision of each ball with the floor is correct? Kinetic energy is conserved for both balls. No, that's not true because the one changed its velocity. The change in momentum of ball P is greater than that of ball Q. Well, let's have a look. Okay, what is the change in momentum? Is delta P, PF minus PI. Now remember, momentum is a vector. So if we go down, what do we want? Do we want up is positive or do we want down is positive? If we say up, let's go up is positive, yes? Okay, so let's say up is positive, okay? So when this ball rebounds, the mass is not changing the same, so we can say mvf minus vi, and we said up is positive, okay? So for ball P, it rebounded upwards with v, okay? And then we subtract the initial velocity, but the initial velocity was downwards, so it's v minus v. So v minus v becomes v plus v, okay? So this one is going to be 2mv. This is ball P. If we look at ball Q, the same thing. It's going to be mvf minus vi. We said up is positive, so my final velocity is a half v, and then we are going to minus negative v because they both went down there with v. So a half plus a half is 1.5 mv. Okay, so are these two the same? The change in momentum for ball P is greater than that of ball Q. This is true. So this looks like it might be my answer. The contact time with the floor is the same for balls P and Q. How would we figure that out? We've got nothing that's going to help us there, I don't think. Momentum is conserved for the collision of ball P, but not for ball Q. No, why can't momentum be conserved for ball P? Okay, so if you look at ball P, okay, ball P had a, if we say up is positive, it had a negative momentum as it went down, and it had a positive momentum as it went up. So is the one before equal to the one after? No, I don't think so, because of the vector nature of momentum. I don't think statement D is correct, which means that the answer must be B. Okay, now we've got another trolley question. Two trolleys, X and Y, of mass M and 2M are held by a compressed spring. Initially they're stationary. Ignore the effects of friction. The spring is now released and falls to the floor while the trolleys move apart. The magnitude of the momentum of trolley X while it moves away is 0. That can't be true because it's moving away, so you've got some momentum. Half the magnitude of the momentum of trolley Y, twice the magnitude, the same. It's got to be the same, because why? This is like an ideal system. So the magnitude, this is what we call an explosion in momentum things. We have one object that separates into two objects, and by Newton's third law, they are equal and opposite. The force that's acting on them is equal and opposite. So the momentum is going to be equal and opposite. What will happen though, Y is heavier, so Y will move slowly and X will move fast. But the product of the mass and the velocity will end up at the same value, but in opposite directions. So the magnitude is the number that will be the same. Now it says an object is dropped from rest. Okay, so we've got the ground here, and we've got our object, and we drop it from rest. And after falling a distance x, its momentum is p. So here is x, okay? And the momentum is p. P is mv. Ignore the effects of air friction. The momentum of the object after it has fallen a distance 2x. So here's my object. We're going to make it fall twice as far. Okay. So here's another x. Okay, so the total distance is 2x. The momentum of the object is going to be what? Okay, so P equals mv. If we look at this v over here and this v over here, this v, the second v, is going to be bigger because the ball's been traveling for longer. Okay, so the mass of the ball has not changed. P equals mv. So the second momentum has to be bigger. So any answer that's the same as P, we're going to ignore this one. And any answer that is smaller, we're going to ignore. So it has to be bigger than P. So is it root 2P or is it 2P? How would we work this out? We need a little bit of help from our equations of motion, okay? So we need an equation of motion that is going to give us a final velocity, okay, and a distance. So if we use Vf squared equals Vi squared, yes, plus 2a delta x, okay? We're going to lose the Vi squared because they were both dropped from rest. So this Vf, now remember, this is giving you Vf squared for 2a delta x. We're going to ignore the 2 because for both times we drop the ball, the 2 stays the same. We're going to ignore the a because for both times it stays the same. So we end up with Vf squared is related to delta x like this, yes? So Vf is going to be the root of delta x. So then, if this ball travels further, okay, so if this was the first one, for the second drop, Vf squared is going to be Vi squared plus 2a 2 delta x, yes? So the same thing happens. This is 0, we ignore it. The 2 and the a stay the same. The VF is going to end up being the root 2 of delta x. Yeah? So what is the difference between this VF, which we use to calculate P equals mv, and this VF? The difference is root 2, so the answer is going to be B, the square root of 2p, because that is how my velocity changed. My velocity for double the distance is the root 2 different. Okay, 1.7. Which one of the following statements is always true for inelastic collisions in an isolated system? Well, in an inelastic collision, what is not conserved? Kinetic energy is not conserved. So I've got 2 here. This one says energy is conserved, so we're going to get rid of it immediately. This one says kinetic energy is conserved, so we're going to get rid of it immediately. So now how do we pick? Momentum and kinetic energy are not conserved. Momentum is conserved. Kinetic energy is not. So in this one, we've got here the isolated system. Yes? So in this one, because of the isolated system, we can pick the answer C. In an isolated system, momentum is conserved. Okay, 1.8, a ball moving horizontally hits a wall with a speed of 2v. The ball then bounces back horizontally with a speed of v. Well, if the ball has decreased velocity, its kinetic energy has also decreased. Okay, so if the kinetic energy decreases, then the kinetic energy is not conserved. So I can see already there's a table about kinetic energy. I am going to cross out anything that says the energy is conserved, because the ball changed velocity, the energy has not been conserved. Okay, now it says to you, which one of the following combinations regarding the linear momentum and the total kinetic energy of the ball for the collision above is correct? Assume that the ball wall system is isolated. Okay, so now this question's given me some trouble. The only thing I can conclude, okay, in this question, it says, which one regarding the linear momentum and total kinetic energy of the ball? If you see here, it says the ball wall system is isolated, okay? That means that both objects, the ball and the wall, are considered together when we consider the system. But this question is asking you only about the linear momentum of the ball. So if we look at the ball before the collision, okay, P equals mv. Momentum is a vector. So if we say to the right is positive, okay, before the collision, this is going to be m2v. After the collision, okay, it is going to be mv, and it's going to be as well minus mv. So those two values, 2mv and mv, because we just rearrange this to be 2mv, those two are not the same. If these two are not the same, for the ball's linear momentum was not conserved. Maybe for the whole system, if you count the wall in, everything is conserved, but for the ball only, the answer is C. Now it says to you, two cars, P and Q, moving in a straight line, have the same momentum. The kinetic energy of Q is greater than the kinetic energy of P. So P equals mv, EK equals a half mv squared. If one of them has got a greater kinetic energy, okay, something must be different with this, okay? So which one of the following statements regarding the cars is correct? So in this one here, okay, the kinetic energy of Q is greater. We've got to see what can we get rid of here. I would get rid of Q is moving slower than P, okay? Why would I get rid of this? because if Q is moving slower than P, it's highly unlikely its kinetic energy is going to be bigger, because it would have to be so small because of the V squared. Remember, kinetic energy is V squared. So now, if the cars, let's look at B now. If the cars have the same mass, okay, they said P equals mv, and the momentum of P is equal to the momentum of Q. So if the mass of P is equal to the mass of Q, the V of each must be the same, which means the kinetic energy is going to be the same, okay? Because if the P's are the same and the masses are the same, then something is wrong. The kinetic energy would have to be the same. So this one we're also going to cross out, okay? So now, if Q was moving at the same speed as P, this is not likely to give us the correct answer, because the energy is changing by the V squared. If we look here, P equals mv, let's try this with, if we go, the P of Q is equal to mv, okay? So if this must be equal to the P of P, which sounds really weird, the momentum of P is equal to the momentum of Q, which is equal to the mass times the velocity. So if we look at Q, if the mass of Q is smaller, then the velocity of Q will be bigger, okay? And than the mass of P and the velocity of P. So this can actually work. This answer A can work, because if we go back into the EK equals a half mv squared formula, a smaller v, but coupled with a smaller m, but coupled with a bigger v squared is definitely going to give you a bigger kinetic energy. So I would say that the answer is A, because at the end of the day, the thing that's going to have the biggest effect here on the energy versus momentum thing is the velocity. So we should do something with the velocity. And the only way to give Q a bigger velocity is with the same momentum is to decrease its mass. Okay, now we've got some more balls colliding with each other. So we don't have a picture, so let's make a picture. Ball M moving to the right at speed V collides with a stationary ball N on a smooth horizontal surface. Immediately after the collision, M comes to rest and ball N moves off with a speed V. Okay, it says to these balls, yes, so this one's momentum was mv, this one's momentum was 0, this one's momentum after the collision is going to be 0, and this is going to be mv. So if this is an isolated system and it says it's on a smooth surface, so we are an isolated system, the linear momentum should be conserved. Okay, so if the momentum is conserved, I would say the masses of the balls have to be equal in this situation, okay? In this situation, the masses of the balls should be equal, because that's usually the only way you can get this collision to move off with exactly the same V. And I would think that this is an elastic collision, yes. So momentum is conserved, kinetic energy is conserved, and the masses of the balls are equal. I like answer C here, okay? Total momentum is conserved, the masses of the balls are unequal. If the masses of the balls were unequal, there's no ways we could conserve the momentum. The kinetic energy is conserved, and the masses of the balls are unequal. You can't... The total kinetic energy, yes, it is conserved, but the masses of the balls are unequal. If the masses of the balls were unequal, the second ball would move off with a different V, and it moves off with the same V in an isolated system where the momentum is conserved. No, the kinetic energy, the last one says the kinetic energy is not conserved, and that's not true. So it has to be answer C, because that's the only thing that's conserving everything. All right, so now we go to 1.11. If the momentum of an object is doubled, okay, P equals mv, then its kinetic energy, which is Ek equals a half mv squared. So now if we are doubling the momentum of the object, okay, it goes from being P to 2P, must be 2mv. And so now they said an object, I think we have to assume the object is not changing its mass. So if we are doubling its momentum, we are changing v is going to go to 2v, because that's the only way to double its momentum if you don't change the mass. So if we then put this into the kinetic energy formula, it's going to be a half of m2v squared, which is 4. So 1.11, the answer is D. The kinetic energy is going to get 4 times greater because 2v squared is 4v squared. Now it says to you, two bodies undergo an inelastic collision in the absence of friction. So an inelastic collision, the Ek is not conserved. The absence of friction talks about the linear momentum in an isolated system is conserved. So if there's no friction, momentum will be conserved. That gives us these two. But in an inelastic collision, kinetic energy is not conserved. So the answer must be B. Now we've got an airbag question. Airbags, Newton's first law. Airbags in modern cars provide more safety during an accident. The statements below are made by a learner to explain how airbags can ensure better safety. Well, how does an airbag work? Okay, an airbag needs this formula, F net delta T equals delta P. Now, when we have a collision in a car, this delta P is going to stay the same. Okay, what is happening? You have got your mass and you have got a final velocity and initial velocity, and your final velocity is going to be 0. Okay, you're not changing your mass in the collision, you're just changing your velocity. So you go from a very fast velocity to 0. So it doesn't matter whether you've got an airbag or not an airbag, this delta P is going to stay the same. So what is the airbag doing? The job of the airbag is to decrease the force by increasing the time of contact, because it takes you longer to get to 0 when your face hits the airbag. So how do they work? They increase the time of impact, yes. The impact force decreases, yes. Okay, those look good. But now what about the impulse increases? No. What is impulse? Impulse is this delta P. That impulse is going to stay the same because you are the same mass in the accident before and after, and your velocity goes from whatever the heck it was, very speedy, to 0. So the only thing that gives me 1 and 2 only is D. Now we've got learners perform an experiment using identical trolleys, each of mass m. The trolleys are arranged as shown in the diagram below. They are initially at rest on a frictionless surface and connected with a compressed massless spring. So this is one of those explosion examples in linear momentum. Okay, so they're on a frictionless surface, so we're going to assume linear momentum is conserved. When the spring is released, it falls down and the single trolley moves to the left. So this trolley is going to move to the right by Newton's third law. The magnitude of the momentum of the two trolleys moving to the right. Okay, they're trying to trick you here. Okay, what's going on here? This is an isolated system. Momentum is conserved. So the momentum to the left is going to be equal to the momentum to the right. Okay, because why? We had 0, the initial momentum before, the sum of the initial momentum before is equal to the sum of initial momentum afterwards. Okay, so this is 0, and then it'll be the one on the left and the one on the right, and because they move in different directions, the one will be positive, the one will be negative. Okay, and then when you bring this negative over the bracket, they become positive and the two sides are equal. Okay, the thing here is what they're trying to trick you with. You know, these two heavy trolleys, the V will be small, and this one trolley, which is lighter, the V will be big. But the momentum is going to be exactly the same value. It is going to be P. Whatever the momentum to the left is, by Newton's third law, the momentum to the right will be exactly the same. We are nearly at the end, which is a good thing. Okay, a pendulum bob is released from point P above a horizontal surface. At the lowest point Q of its swing, it collides with a stationary block situated on a frictionless horizontal surface as shown below. Ignore air friction. Okay, so whenever we see a pendulum, we are usually using the law of conservation of mechanical energy. So we know that at this point, the pendulum is full of potential energy, and at this point it's full of kinetic energy, and the energy is conserved. So how would we find the speed at Q? If we knew this height h, we could easily work it out. So the answer to finding the speed at Q will be the conservation of mechanical energy. So this gives us A and C. We can't use linear momentum for the first part because it's only one object and it's not colliding with anything, okay? But in the second part, can we use the conservation of linear momentum? Yes, we can use the conservation of linear momentum, which is answer A, okay? Because we've got two objects, and the momentum of object Q before the collision plus the momentum of the block before the collision will be equal to the momentum of Q plus the block after the collision, because they are now together, okay? We can't use the conservation of mechanical energy here, okay? It won't really work very well. But linear momentum we can. Why can't we use mechanical energy? Maybe under special circumstances we can, but it's more likely you're going to use the conservation of linear momentum because there has been a collision. You could possibly try the sum of the mechanical energy, but definitely I would say that A is your safer choice. Okay, now we've got this question, which is also in the projectile motion questions that I did. The diagram below shows the section of a path of a stone projected vertically upwards. At which one of the positions indicated on the diagram will the magnitude of the momentum of the stone be the greatest? Okay, so P equals mv. We are not changing the mass of the stone, so we want to look at the velocity of the stone. How will we get a big momentum? We will get a big momentum with a big velocity. So we know if this is a projectile, okay, the velocity at 1 will be equal to the velocity at this point here, okay? These two velocities will be equal because of symmetry of motion. At maximum height, the velocity is going to be 0. So the projectile will have no momentum at maximum height. And then here, as the ball drops, where's the greatest velocity? It's going to be at 0.4. So that has got to be where my momentum is the greatest, because the mass of the ball is not changing, and P equals mv, so we look for the biggest v. Now it says to you, when the velocity of a moving object is doubled, what will be doubled? Network. Network is the change in the network done on a system is equal to W net equals delta EK. No, if we change the velocity by doubling it, okay, the change in kinetic energy will not be doubled because EK is a half mv squared, so this will be 2v squared, which is going to be 4v squared, okay? So then the network is not going to double, the network is going to change by 4 because the kinetic energy changed by 4, so that answers also out. The potential energy is doubled. Potential energy depends on where you are relative to the surface of the Earth. We know absolutely nothing about this. The ball would need to be going upwards to actually double its potential energy, and that's just not going to happen. So it must be the linear momentum of the object is doubled, yes, because P equals mv. If we don't change the mass and we go m2v, then this must be 2p. So 1.1.7 must be D. That must be the correct answer. Now this one here is a definition. The rate of change of momentum of an object is equal to. So change of momentum is impulse, which we call delta P. So we have a formula that says F net delta T equals delta P. It is on your data sheet. So the rate of change of momentum, when you see the words rate, it means we are going to divide by the change in time. So let's go. The rate of change of momentum in symbols is delta P. Change in time is delta T. So that leaves us with F net, yes? So the rate of change of momentum is equal to the impulse. No, it is not, because impulse is not the rate of change. It is just the simple change in momentum. The net force, yes, this looks like my answer from the formula. The product of the body's mass and change in velocity, no, that is still impulse. It's got nothing to do with time. The product of the net force acting on an object and its acceleration, no. Force times acceleration is going to give you something quite scary, but it's not going to be the rate. Okay, so the answer there is B. Now, the last one, a ball of mass m falling vertically downwards hits the floor with a speed v and bounces vertically back upwards with a speed of 0.75 v. Which one of the following combinations regarding the change in momentum of the ball during the collision is correct? So the change in momentum is our friend delta P, which is mvf minus mvi, which we can put as mvf minus vi, yes? So, what is the change in momentum? If we have a look here, if we say, what shall we say? Shall we say up is positive? Because this question is tricking you, because you must remember that momentum is a vector. So if up is positive, my change in momentum is going to be 0.75 minus because that was my final velocity, minus my initial velocity, which was v, but that initial velocity was in the opposite direction, so it is also minus. So 0.75 v, sorry, this is not 0.75, it's 0.75 v. 0.75 v minus v is 1.75, okay? And the change in momentum, this is a positive value, it is going to be upwards. So this answer has got the right magnitude, and this answer has got the right direction. So because we said up is positive, my answer was positive. There we go, 1.19. The final answer here is going to be C.